3, 2, 1. Hello, everyone. Welcome to this talk as part of the ALMA Recounts of Cosmic Conundrums series. It is a great pleasure to welcome you today to this series organized by the European Art Network. My name is Gergo Popping. I'm at ESO, and I will be chairing the session for today. So the European Art Network consists of a number of nodes distributed throughout Europe, coordinated by ESO. And the main goal is to maximize ALMA's scientific return to the European users. And this includes providing virtual or real-life user support to anyone that wants to use or get to know more about ALMA, or needs to support with data calibration and analysis, proposal preparation, etc. But it also includes organizing talks like today to really celebrate and promote ALMA science carried out in Europe, and to stimulate new interactions and build new connections. Today, we are delighted to have with us Izaskun Jiménez-Serra, who will address the question, how are the building blocks of life formed? So Izaskun did her PhD in Madrid, after which she took up a position as a postdoc in Leeds. She then held multiple fellowship positions, first an SMA fellow in the US, then a Marie Curie fellowship at ESO, and she was then an STFC Ernest Rutherford Fellow at the University College in London and at the Queen Mary University in London. In 2018, Izaskun joined the Centro de Astrobiología in Madrid as a staff researcher, where she has been ever since, studying prebiotic molecules in the interstellar medium and massive star formation in the Milky Way. Izaskun is really an expert in astrobiology. She was a co-chair of the Cradle of Life and Astrobiology Science Working Group for the Square Kilometer Array. And she's a frequent user of various submillimeter interferometers. And I thus really look forward to her presentation, where she'll explain us about ALMA's contribution to our understanding of the building blocks of life. Izaskun, the floor is yours.
Thank you. Thank you very much for the very kind introduction. Thank you very much for the kind invitation. Really, it's a pleasure to be here with you today. And it's really great that I have this opportunity to show you the science that we are doing at the Astrobiology Center in this interesting topic about the building blocks of life, and how we can provide some answers or some hints about how that complex process happened or occurred on our Earth. So, but before I move on, what I would like to do is to mention where the Astrobiology Center is, because I know that some of you are not familiar with this institute. So it's a relatively new institute. So it's we celebrated the 20th anniversary just a couple of years ago. And so it's a multidisciplinary center. So we have biologists, geologists, chemists, biochemists, engineers. So as you can see, it's very stimulating from that point of view, because there are many people working on many different fields. And I belong to the astrophysics department, and in particular to the interstellar medium group. And I'm actually quite happy that in the past few years we have been able to accrete or to attract young people who are actually the ones pushing forward the research that we are trying to do on the detection of new prebiotic molecules in interstellar medium. And in particular, I would like to mention Victor Rivilla, Laura Colsi, and Juan Garcia, who are actually deeply involved in this type of research. So the interaction with members of other departments has been quite fruitful so far. We are collaborating with researchers from CAB, from the Astrobiology Center, such as Carlos Briones, who is a biochemist and an expert on theories of the primordial RNA world. He has actually provided a lot of input for some of the works that I'm going to be mentioning today. And also David Hochberg, who is an expert on the origin of homochirality for amino acids and sugars. So this interaction is actually, as I said, very stimulating. We also work with other people from other institutions, so either astronomers or spectroscopists or material physicists. And I would like to mention in particular the very important work that spectroscopists are doing at the moment, because they are providing the key information that we really need to search for these prebiotic species in the interstellar medium. And without them, we wouldn't be able to actually report or to have done to have reported the new detections that I'm going to be mentioning today. But if we want to understand how the building blocks of life form, so we first need to understand, or first need to have a look at what life is. And according to NASA's definition, life is a self-sustaining chemical system capable of Darwinian evolution. Then this very simple sentence actually contains the three basic properties of life. So it's a chemical system, or it has to be a chemical system, which means that it has to be compartmentalized. So it should have a membrane within which all the genetic information can be stored and can be preserved, and also where the metabolic processes can take place. It also has to be a self-sustaining system. So that means that it has to be able to perform the metabolism. So it has to be able to perform the metabolic processes. And also it should be able to follow Darwinian evolution. So this means that it should have some kind of mechanism to store and to transfer genetic information. So all these three are the basic properties of life. Now, at the origin of astrobiology, the first theories that were proposed focused either on one of, or focused only on one of these three properties. So some theories were saying that compartments came first, membranes came first. Others were proposing that metabolism came first. And some others proposed that the storage and the transfer of genetic information came first. So these RNA molecules, for example, came first. Now, there's an emerging picture within the past few years that it is called the prebiotic systems chemistry, that is proposing that all these three different properties should have emerged simultaneously at the same time. So in this theory, in this scenario, what they are proposing is that there must have been a high diversity of precursor components already available on a prebiotic Earth, on the surface of Earth, and that those components turned progressively into primordial metabolic, self-replicating, and membrane-bounded subsystems. So this means that in this scenario, so we would start with these very simple precursors, these very simple molecules that self-organized and then started producing or generating these subsystems, each of them performing the different properties of life. And then at the end of this process, then we find the formation of the first cell, living cell, or the LUCA, what it is called the LUCA, the last universal common ancestor that we all come from. So as astrochemists, we are interested in these first steps. So we focus on the precursors that led to these smaller subsystems that were key for the development of the first biochemical processes that led to the origin of life. So in astrobiology, there are two main lines of thought. One of them assumes that these prebiotic compounds or these precursors formed on the surface of Earth endogenously, so they formed on a kind of primordial soup. And then there's a second way, or the second line of thought, which proposes that at least fraction of that prebiotic material could have arrived from outer space, so that it was formed exogenously, and it arrived through the impact of meteorites and comets during the late heavy bombardment period that occurred between 4.1 and 3.8 billion years ago. So this is the last, or this latter scenario is the one that we have taken as our work hypothesis. So our work hypothesis is that a fraction of that prebiotic material could form already in the stellar medium. It could have been transformed, or it could have been transferred to these planetesimals, to meteorites and comets, and then they could have brought all these prebiotic contents to the surface of an early Earth. Now, there has been some experiments that have shown that this prebiotic material not only survives the entrance of the atmosphere, but it also survives the impact that they experience on the surface of Earth. And they not only survive, but they also produce even more complex species. So this is something that it is fully plausible, and this is what we are considering for our research. Now, this is the outline of my talk. So first I will start introducing what a complex organic molecule is, because you've probably heard of this kind of species, and actually the prebiotic precursors are complex organic molecules. So they actually represent the connection between the simple chemistry that we find in the interstellar medium and also the more complex chemistry involved into biochemical processes. I'll put it into the context of the new detections of these prebiotic complex organic molecules done by ALMA. And also I will present some of our recent results in this line of research. And then I'll try to finish my talk by presenting some of the perspectives, or what I think, my personal view of what this field should move toward in order to try to understand better how the building blocks of life formed. Okay, so complex organic molecules, so they are defined for us astrochemists. So they are defined as carbon-based compounds with at least 6 atoms in their molecular structure. And within these complex organic molecules, I like to define a subset of huge combinations of complex organic molecules and variety of complex organic molecules. I like to define that subset that we call prebiotic compounds, which are the ones that we believe they could have been involved in the processes leading to the origin of life. So some examples for those prebiotic COMs could be glycolaldehyde, which is actually the simplest form of sugar that we know of. The next one in complexity, in increasing complexity, is glyceraldehyde. Then another very important molecule is urea, as I will show you later on, or glycolaldehyde. So these type of molecules are the ones that I'll be referring to when I talk about prebiotic species or prebiotic compounds. Now, how are these complex organic molecules formed in the interstellar medium? It was around the 2000s, early 2000s, it was realized that methanol, which is the simplest complex organic molecule, and thanks to experiments, it was realized that it could not form in the gas phase. So the other possible mechanism that could yield or that could produce methanol in the interstellar medium was on the surface of dust grains, because dust grains can act as catalysts. Then it was then proposed that 2 main mechanisms for the formation of these complex organic molecules, either via hydrogenation, which means that hydrogen is highly mobile on the surface of dust grains, and then once it moves on the surface, it can encounter either heavier atoms or radicals, and this leads to the formation of complex organic molecules. Then the other possible mechanism that was proposed was the radical surface reactions. In this scenario, the temperatures have to be higher than 30 Kelvin because it requires the mobility of radicals on the surface of dust grains because they are heavier. Then they need higher temperatures to move around on the surface of the dust grain. So once they encounter, they react, and then they form complex organic molecules. However, the advent of new instrumentation and higher sensitivity instrumentation in particular showed that these complex organic molecules are prevalent in the interstellar medium and across many different types of environments. In particular, it was found that these complex organic molecules were also present towards regions that presented the coldest conditions in the interstellar medium, such as molecular dark cloud cores, prestellar cores, starless cores. So these really represented a challenge for the traditional theories for the formation of complex organic molecules. So there was, and there is still, a huge activity within the community to try to explain or to try to propose mechanisms that can explain the formation of these complex organic molecules, especially under these very cold conditions in the interstellar medium. Then it was one of the alternative possibilities is that these complex organic molecules form in the gas phase. And here I list some of the works that have focused on this particular scenario. And here I show the case of this paper by Dimitris Skouteris from 2018, where he, by starting from ethanol, so he can actually explain the formation of other complex organic molecules such as acetic acid, acetaldehyde, glycolaldehyde by using or through these neutral gas phase reactions, especially under these very cold conditions. On top of this, on top of the gas phase formation, there have been other mechanisms proposed, which are the ones that I list here. So either non-canonical explosions on grains, cosmic ray-induced radical diffusion, impulsive spot heating on grains by cosmic rays, sputtering of grains by cosmic rays, or the non-diffusive in situ formation of grains. In this particular is the one that seems to have attracted a lot of interest in the community in general, because what it assumes is that radicals are formed in situ, so within the same dust grain site, so they don't need to move on the surface to actually react and then create more complex molecules. And this is the work led by Harold Leenaerts in Leiden, and who has recently been implemented theoretically in a theoretical scheme by Rob Garrott. So these are the different mechanisms that have been proposed for the formation of these complex organic molecules in the terrestrial medium, especially relevant for the very low temperatures. The truth is, regardless the mechanism or the formation process for these complex organic molecules, that these organics or these complex organics are found in many different types of environments in the ISM and across the ISM. So they are found in star-forming regions, in hot cores or hot corinos, so in these dusty cocoons around massive protostars and low-mass protostars. They are also found in molecular outflows, even in the harsh environments of photon-dominated regions where these complex organic molecules should be destroyed by the intense UV radiation fields. They have been found, as I mentioned before, under these cold conditions in molecular dark cloud cores or interstellar cores or starless cores. And also they are known to be very abundant in the giant molecular clouds located in the galactic center. So as you can see, so they can be found, they are ubiquitous in the interstellar medium, so they can be found under very different types of environment and with very different physical conditions. So star-forming regions, and in particular hot cores and hot corinos, were the prime targets for the search of these complex organics in the interstellar medium for the reason that they are chemically very rich. So these dusty cocoons or these environments, so complex organic molecules are very abundant on the mantles of dust grains, and because of the high temperatures that these sources present, so these mantles are released, are evaporated, and then they are incorporated into the gas phase, and that's why we see these high levels of chemical complexity, of chemical richness. So that's why they have represented the main targets for the detection of complex organic molecules and also of prebiotic molecules, as I'll show you in a bit. And for this, ALMA has represented a revolution in this field because it has performed these broad bandwidth, high sensitivity surveys towards these type of sources. So either, and I can mention these two surveys, the PIL survey and the MOCA and REMOCA surveys carried out towards the hot Corino IRA 16293, or the hot molecular core Sagittarius B2N. These surveys led by either Jorgensen for the PIL survey or Arnaud Beloche for the MOCA and REMOCA survey. So they have reported a huge variety or a huge number of these complex organic molecules and prebiotic species in this kind of environment. And I can mention, for example, for the PIL survey, glycolaldehyde was first detected towards this hot Corino. So there was a previous detection towards a hot core by Maite Beltran, but this was the first time glycolaldehyde was reported towards a hot Corino. Also formamides, the same case, methyl isocyanates, the first detection in the interstellar medium, glycolaldehyde, also también the first detection, acetamide and acetic acid were also detected here for the first time towards a hot Corino, low mass protostar. For the MOCA and REMOCA surveys, what Arnaud Beloche and his group has provided was the detection, for example, of the first branched molecule in the interstellar medium, isopropylcyanide, urea, very important prebiotic molecule, or N-methyl formamide. And I would like to mention also the results that are coming out from the WAPO survey towards this hot molecular core, G3141, where I would like to mention the work of Laura Colzi, where she has also performed a study of the inventory of peptide-like bond molecules towards this hot Corino and put it in context with the other sources where this type of molecules has been reported. Then from all these results, what I would like to, the one that I really personally I like very much is the detection of this first branch molecule in the interstellar medium, this isopropylcyanide, because these represented a step forward in our understanding of how these molecules or these branched molecules could form in interstellar medium. And this has important implications for our understanding of whether amino acids can form in the interstellar medium, because amino acids show this kind of branched structure. So I think this was a very important result for astrochemistry and for our understanding of how these prebiotic species could form in interstellar space. Another very nice result was the one of the detection of urea, which is a key prebiotic molecule, in particular for the formation of ribonucleotides, as I will show you later on. And although not all these performed with ALMA, and although not performed with ALMA, I would also like to mention the detection of propylene oxide by Brett McGuire in 2016 using the GBT, which was the first detection of a chiral molecule also towards Sagittarius B2. So as you can see, so this type of sources have been really prolific for the detection of new prebiotic species in interstellar space. Now, in the past few years, however, there has been a shift in the field, and some groups have decided, instead of focusing on these hot sources, which present some disadvantages, such as the high level of line blending and line confusion that the observed spectra show. So they have decided to target instead colder sources, such as molecular dark cloud cores, because these sources, they present very low excitation temperatures. And then that means that because these excitation temperatures are very low, the level of line confusion is much lower, because only the lower levels of the molecules can be populated. And therefore, there's going to be also less contamination from lighter, less complex molecules. And that's why they have decided to perform these very deep integrations, these very deep surveys towards this kind of sources. And for this, I would like to mention the amazing work that all these two groups are performing at the moment. The first one is the group by Brett McGuire using the GPT on TMC1, and also the group of Pepe Cernicharo using the Jeves 40-meter telescope also towards the same source, TMC1. And they are reporting all these amazing detections of these ring-like molecules that are actually aromatic molecules that are precursors of PAHs. So here I just list some of the examples of the most complex species that they have been reporting in the past couple of years. And as you can see, it's really amazing that we see these molecules, these complex and large molecules being formed even at these cold conditions in the terrestrial medium that we don't even know yet how these molecules, these complex molecules form, but it is definitely something, the challenge to really investigate in the future how these large molecules are formed under these extreme conditions. So, and now what has been our approach? So our approach is slightly similar. So what we have been doing is we have been focusing on also sources that present their molecular emission presents low excitation temperatures. However, we know that they show a very high level of chemical complexity, and that's why we have decided to target this type of sources instead of the others that I mentioned before. So these targets are the giant molecular clouds located in the Galactic Center, and as I'll show you here, so this is a map of the central molecular zone, and this was the first works were performed by Jesus Martin Pintado and collaborators who decided to target a few of these giant molecular clouds across the central molecular zone and then investigate the level of chemical complexity. And what they found is actually that all these GMCs, or these giant molecular clouds, presented a similar level of chemical complexity, and that they show very high abundances of these complex organics wherever they looked at. In particular, they found this giant molecular cloud, which seems to be one of the richest reservoir of complex organics in our galaxy, the GMC, or the giant molecular cloud G0693. And we selected this cloud because it is quiescent in the sense that there's no sign of star formation activity. Then the physical conditions of this cloud are the following. So it shows the H2 density is relatively low compared to star forming regions, so the order of 4 times 10 to the 4 particles per cubic centimeter. Then the temperature of the dust and the gas is decoupled, so the dust temperature is lower than 20 Kelvin. However, the gas temperature is high, so it ranges between 70 and 150 Kelvin. However, because of the densities are very low, the molecular emission shows very low excitation temperatures, and these really represent an advantage for the search of complex organics in crowded spectral surveys, such as the ones that we are obtaining for this source. So this is really the key for this source, that it has the molecular emission of complex organic molecules shows very low excitation temperatures, and this really reduces largely the level of line confusion and line blending in this spectral surveys, in the spectral surveys that we are carrying out towards this source. So these are the examples of the surveys that we have performed so far. So we have performed a very deep survey, initial pilot survey with the Jeves 40-meter telescope covering the Q band, so from 30 gigahertz to 50 gigahertz. Also, we have performed spectral surveys at 3 millimeter and 2 millimeters, and now we have some data also at 1 millimeter. And from all the studies, all the analysis of these data sets, so what we have found so far is that we have detected more than 120 species, and out of which 50% of them are complex organics. So we could say that this giant molecular cloud is probably one of the most important reservoirs of complex organic molecules in our galaxy. The peculiarity of this source is that it is rich in complex organics, but from different families. So it is rich in oxygen-bearing complex organic molecules, also in nitrogen-bearing complex organic molecules, and even in sulfur-bearing complex organic molecules, as I'll show you later on. So it is an excellent target to perform these deep searches, or these new searches for, or the searches for the discovery of new prebiotic species in the interstellar medium. Now, how did we tackle these searches of prebiotic species? So what we decided to do was to first focus on one of the properties of life within this prebiotic systems chemistry theory, which is the part of the genetic storage and transfer. For this particular one of the most accepted theories for this property of life is the primordial RNA world, which proposes that RNA molecules were the first ones appearing because they could store genetic information, they could replicate genetic information, but they also could perform the first metabolic processes. The only thing that they could not perform was the formation of membranes, and that's why there has been some criticism with respect to this theory for the origin of life. So what we did was to consider, or to take the different chemical schemes that had been proposed for this primordial RNA world. And here I would like to mention the work of the group of Sutherland in Cambridge with the papers, the main papers here, the one from Pauner in 2009 and Patel in 2015, were starting from very simple molecules, so they could build up the first pyrimidine ribonucleotides, which are the basic building blocks of RNA, but they could also build up amino acids and also sugars and lipid precursors. So they could build up all this whole chemical scheme to try to obtain these first building blocks required for this primordial RNA world theory for the origin of life. Something that really encouraged us to continue this idea was the detection of glycolaldehyde, which we performed using ALMA towards IRA 1693, and this is the work done by Sandy Zeng in 2019, where this molecule actually represents a key intermediate species in the production of sugars with 3 and 4 carbon atoms. So this is the detection reported by Sandy towards IRA 16293, and now, so there is a recent paper also by Lichtering in 2021, where they reported also the presence of these molecules towards serpents SNN1 as well. So this molecule seems to be common also in the interstellar medium in this type of environments. So by following this, so this chemical scheme, so in blue, I just put the molecules that have been already detected. And what we decided to do was to focus on these other 4, on urea, 2-aminoxazole, glycolaldehyde, and dihydroxyacetone, which at the time when we started had not been detected. Urea was then later on detected by Arnaud Beloche, so he was first, but we decided to look for this species. So for the case of this species, glycolaldehyde and dihydroxyacetone, we did not detect it, so we reported upper limits, and this was consistent with previous searches towards Sagittarius B2N. In the case of urea, so we did detect this species, so this is definitely present in this giant molecular cloud, and it shows abundances of the order of 5 times 10 to the minus 11. So here you can see the type of abundances, very low abundances that we detect of these complex organic molecules, of these prebiotic molecules. So this gives you an idea of how deep we really need to integrate. We really need to go into the observed spectra in order to see these prebiotic species. And we also tried to obtain 2-aminoxazole, for which the microwave spectroscopy was available. So we obtained these upper limits of the order of 10 to the lower than 10 to the minus 10. Now, regarding 2-aminoxazole, is actually one of the key intermediates for the production of ribonucleotides, the pyrimidine ribonucleotides. So this actually triggered some interest in the material physicists in the group of Belén Maté, also from Madrid, from the Instituto de Estructura de la Materia. And what they decided to do was to study how 2-aminoxazole behaves to the reprocessing of pure and mixed ices of 2-aminoxazole and their irradiation. So either UV irradiation or by using electron simulating the impact of cosmic rays. So in this way, they could obtain the photodistraction rates, and they could establish that 2-aminoxazole in principle could survive in ices and or in dense molecular clouds for times longer than 10 to the 8 years. However, if 2-aminoxazole were present in objects in a protosolar nebula, it would be readily destroyed. So this actually posed some doubts or some skepticism about this molecule being one of the key intermediates for the formation of these pyrimidine ribonucleotides. Alternatively, later on, or after the theory proposed by the group of Sutherland, there was this very nice work led by Thomas Carroll from LMU, from Munich, from the group of Thomas Carroll from LMU, where they proposed that they could form at the same time pyrimidine and purine ribonucleotides by starting from very simple molecules such as formaldehyde, HCN, but also these other ones, urea and hydroxylamine. Then urea, so we knew already that urea was present in interstellar medium thanks to the detection reported by Novelos and our detection towards G0693. So the next natural thing to do was to look for hydroxylamine in this molecular cloud. And this is the work done by Victor Rivilla, who published the first detection of this molecule, and the only one I think so far that we have for this molecule in the interstellar medium, where they reported the detection of these transitions, the 2-to-1, the 3-to-2, and the 4-to-3 transitions of this molecule towards this cloud, including also the satellites due to the hyperfine structure. So this was we were very happy because of this result, and then we decided to start looking for other amines, given that this giant molecular cloud was definitely very rich in this type of these compounds with the amine group. And this led also to the detection of ethanolamine, which this is also work led by Victor Rivilla. And ethanolamine has the peculiarity that it actually represents, or is the simplest phospholipid head group. So here we are showing the structure of a typical cell membrane. So this is the actual cell membranes, and here you see the structure of a phospholipid, one of the two types of phospholipids, where ethanolamine is the head group. Then we have a phosphate, a glycol molecule, and also the hydrophobic tails, which are carboxylic acids. Then ethanolamine. So we reported the detection of ethanolamine towards this giant molecular cloud, and with an abundance of the order of 10 to the minus 10. And this is the detection. So these are the transitions reported in this paper that we published in PNAS. And we also could determine the ratio between ethanolamine and water in this particular cloud, and it was actually consistent with that found in the Alma-Ata Sita meteorites. So this finding opens the possibility for ethanolamine being available in early Earth conditions, so that it could have been incorporated into the first cell membranes that appeared on Earth. So this was a very exciting result. And I think it provides new avenues for prebiotic, for studies of prebiotic chemistry led by chemists. Then, besides ethanolamine, we have also reported other detections, such as the cyanamidyl radical, which is a precursor of cyanamide and formamidine. So other species also involved in the formation of other prebiotic compounds. We also have expanded the family of peptide-like molecules with the detection of ethyl isocyanates. We have also reported the first detection of thioformic acid, and thiols are believed to be catalysts in the synthesis of proteins, of prebiotic proteins. And also we have also recently reported the detection of vinylamine and ethylamine, which are believed to be precursors of amino acids. So all these molecules start providing pieces of the puzzle of the prebiotic species that we could form in the interstellar medium. So I think this is very exciting, and we are working on more of these species to be detected in this cloud. So we hope we can provide some more pieces to this puzzle in the future months and years. Of course, this has also triggered other related works, because with the detection of these molecules, so we do not know much about their chemistry. So this has triggered studies, theoretical studies of how some of these prebiotic COMs can form, or how they can experience chemical processes such as the isomerism, so the differences in the trans and cis ratios, abundance ratios for some of these molecules, and also how these molecules could form on the surface of dust grains and also in the gas phase. So, and here I mentioned these works here. So if you want to have a look at them, you're very welcome. Now, so I think I'm just have the 3 minutes to finish. So what is next? Okay, so what we are doing at the moment, so we are performing an even deeper spectroscopic survey towards this cloud in the Q band, again, between 30 and 50 gigahertz. So this is something that we are still getting data. So we are still analyzing the data, and our goal is actually to reach RMS noise levels of the order of this below the millikelvin. So we are reaching sub-millikelvin RMS noise levels. So this is exciting. So we hope we can come up with more detections of these prebiotic species. And also what I would like to mention is what are the perspectives for instruments such as ALMA and for interferometers. So, and I think something that they can provide in the future is these spectroscopic surveys at low frequencies, but performed against bright background continuum sources. And this is something that you may have seen today on the archive. So I posted yesterday. So I was asked to actually provide some insight about the RNA-world and how instruments such as the SKA could contribute to this line of research, but this could easily be applied to ALMA. So the idea basically is that if we have this extended source that is very rich in complex organic molecules, such as G0693, because it is very extended, it's a giant molecular cloud, and we have this bright continuum source, such as for example, it could be a bright H2 region, such as the one located very nearby, very close to G0693, then we could perform these spectroscopic surveys, but in absorption. Then the advantage of this is that we gain the signal to noise ratio for for the molecular transition, for the detection of the molecular transitions. So in this particular case, for this particular paper, so I focused on the frequencies covered by the SKA. But one needs to consider that if we move to the Q band, then these transitions are expected to be more than a factor of 10 brighter. And for these, ALMA band 1 is going to be covering an excellent frequency range where we could perform these detection experiments, or the searches where we could perform deep searches for the detection of new prebiotic species, even more complex than what we have found so far, and we could perform it in absorption. So here in this particular case, I just suggested the case of sugars, because glycolaldehyde, the hydroxyacetone and erythrulose, so they are sugars with 3 and 4 carbon atoms, so they are already quite large and quite big. But if we performed these deep surveys, these high sensitivity surveys against this bright continuum background, we may have a chance to detect them. And just to finalize, so just to summarize, the precursors of prebiotic systems chemistry, they form in interstellar medium. Then what we are suggesting is that these low or these sources with low excitation temperatures present advantages, a lot of advantages for the search of new prebiotic species in the interstellar medium. And also, what I think we should do in the future is to perform these searches but at low frequencies. And for this, ALMA band 1 is actually is going to be a key instrument for this type of science. And then just to add a final note, so we have within the National Research Council, there is now a new initiative in which we are trying to collect, or we are trying to attract the different groups nationwide who are interested in topics related to the origins, coevolution, diversity, and the synthesis of life. In particular, so we have written this white book for the National Research Council, and in which there's one of the challenges is to try to understand the origins of life, and this is this challenge is led by Carlos Briones and myself. So we are having our first workshop next week. So this is really exciting. So we think that we are hoping is to get people together from different disciplines that start talking the same language, and then move forward in this complex, in trying to resolve this complex question of the origin of life. And with this, I finish, and I'll be happy to take any questions.
Thank you very much, Izaskun, for this wonderful talk. I invite everyone to leave their questions in the chat on the right-hand side of your screen. Before going to the questions, I wanted to quickly announce activities organized by the European Arc Network in the upcoming month. There will be an iTrain session on writing and reviewing ALMA proposals on the 18th of March at 11 in the morning, Central European Time. So the nodes in the European Arc Network are all organizing various proposal preparation events in March and in April. We encourage everyone who's interested, who's planning on proposing to attend one of these. So more information on this can be found in the European Arc newsletter, but also on the European Arc webpage under agenda. There will be a European Arc Community Assembly on March the 25th at 11 a.m. Central European Time, following the call for proposal, which is planned to go out the day before. Then lastly, the next ALMA recount of cosmic conundrums will take place on April 6th by Alvaro Haka, who will address the question, what is the role of filaments in star formation and how are they shaped? So all these activities, you can find them in the European Arc newsletter, but also in the agenda located on the webpage of the European Arc. Then let's go to questions. So I have a first question. Thank you for the nice talk. So you provided an overview of locations where various prebiotic molecules are found, like PDRs and outflows, Galactic Center, etc. So I understand that the various locations correspond to different ISM conditions that allow the formation of these molecules. But these specific conditions may be very different from the environments of known exoplanets or even Earth. So how do I couple this together? Does the formation of stars and subsequently planets go through all the ISM phases that are probed with the various locations you study, or does this imply something about traveling of molecules, etc.?
Okay. Right. Okay. So The first type of sources that I mentioned, which are hot cores and hot corinos, those are associated with the star formation. No, so those are locations where solar system or planetary systems are going to form. No, so our solar system is believed to actually have formed in a high mass star cluster. So I think those are actually quite relevant for this topic. Then for the other type of sources, then in our case, so we are focusing on the Galactic Center, because so what we want to understand is how complex can the chemistry of the ISM become, so under these extreme conditions. So our I'm really sorry, I apologize. So this is what happens when one does telework. I'm really sorry. So yes, so let's go back. So that's our goal. Our goal is to understand how far can the chemical complexity go in the interstellar medium. Now, you need to think of a process of the star formation, especially, even for low mass protostars, is not a quiescent process. And it actually goes through, many different stages, very violent stages. No, so we are witnessing, for example, the detection of these complex organic molecules in these FU Orionis type of protostars, where we see these complex organics rising or evaporating from the mantle of dust grains in protoplanetary disks. So we need to consider, or even in some other cases, for example, it has been proposed that these low mass protostars can also generate an intense field of cosmic rays. So what I'm trying to say is that by using this template of these giant molecular clouds in the galactic center, so we can understand how the chemistry can evolve or can flourish under these different physical conditions. Even if we go to the coldest conditions in molecular dark cloud cores, in TMC1, for example. So it's really amazing. It's really surprising that under such, with so little energy available in the system, you can form these ring-like structures. No, so this is our approach. No, so our approach is to try to understand how these complex organics can form under these very different physical conditions, and how far we can go with the chemistry in the ISM.
I was muted, apologies. Thank you. There's another question. So what sets the current developments in this field, especially when looking at the very rich data sets with numerous lines? Is it the theoretical and laboratory work to identify which molecules to target, or is this the instrumentation and time to actually target all possible molecules? Okay, so in our case, I think it is a joint effort here. So I think we need, of course, the work of spectroscopists, because that's really the bottleneck. So we cannot really look for a molecule if we don't know their rotational spectrum. That's the basic thing. So if we don't have the spectrum, then we cannot look for the molecule. And one needs to consider that some of these molecules are actually very difficult to produce in the lab. So to synthesize in the lab, so that they can be, studied, the microwave spectrum can actually be obtained. But of course, we also need the work of material physicists, so to try to understand what are the type of molecules that can be produced under certain conditions in the ISM. So to be able to foresee or to predict what type of species we can expect to find under interstellar conditions. So I think it's a joint effort for the development of new instrumentation. I think ALMA Band 1 can be a very good, an excellent instrument to do that. I personally believe that if we go to lower frequencies, we gain in the sense that the spectrum, the observed spectra, is going to be much cleaner, especially if we go to these low
excitation temperature sources. So I think, so it's the combination of all these aspects is important to move forward in this field.
Okay, thank you. I actually had a question myself following up on this. What you said, you need to know what you're looking for in the data set. So the examples that you showed, they're very rich in lines. I mean, maybe it's hard to put a fraction to it, but in such a typical rich spectrum, how many of these lines are known versus not known, or what is?
We haven't quantified.
Are we talking about 50-50 or very different? I don't know.
Yeah, for our case, for our cloud, I think we have not quantified how many of the lines are still unidentified.
Okay.
So yeah, we haven't quantified that yet. But I mean, I can say that there's a significant fraction that are still unidentified, and we don't know what they are.
No, okay, no, fair enough. I already thought it would go in that direction. Okay. Okay, let's have a look if we have other questions coming in. We don't. If not, then I'd like to thank you again very much for your presentation today and for giving such a broad overview on this topic and also what the prospects of the next couple of years holds. Thank you very much. I thank the audience for participating, for asking questions. If you have any questions about future events or would like to make use of the support of the network, just write a help desk ticket or get in touch with your local node. And we look forward to seeing you soon at a different occasion. Thank you very much.
Thank you. Thank you very much for the invitation. Thank you.
Okay.